have codes for that. All right. Oh, wait, might be off. Oh, it is off. Didn't even turn it on. There we go. All right. Okay. So today we'll be covering backpropagation. And this is going to continue the first advanced workshop nicely. So if you remember, in the first workshop, we kind of explained how does a network learn. So what we would do is we would have some loss function, as you can see here. We would have some parameters W1 and W2, and then each of those parameters is going to be updated in this mechanism we call the gradient descent, where the current value of the weight is going to be updated by the learning rate multiplied by the partial derivative of the loss function with respect to the parameter we're updating. And again, this is a gradient. It's really just a multidimensional derivative with respect to each of these variables of our function. And so if you remember from this slide, it says that we are using something called the chain rule. Because in networks that may be a lot bigger, say if they had 50 or 100 layers, and they had a lot of parameters, calculating the loss of a parameter or the derivative of the loss with respect to the parameter is going to be very complicated. So what we do instead is we devise this algorithm, or not we, there's this thing called chain rule, which we can take the advantage of. Because if you think about it, all of the operations in a neural network can be summed up that it's an f of g of x. So you would have g of x, you can think of it as the input layer. You would put x into g, and then the output of that function will be put into f, which is another layer that's going to create our output. And so to take the derivative of that, we just have this simple rule where h of x is a f of g of x, and then we would take the derivative of h of x by taking derivative of f inside of g of x, and then that multiplied by derivative of g of x. And now this does look a little bit complicated. It's not really intuitive, actually. It's not complicated, but it's just not intuitive. So there is a better example. So to do that, let's first imagine a very simple network. And it's not really a network, it's really just two operations. So we have W1, which is our weight 1. We add x to it, and then the result of that, we're going to multiply by W2. And so I explained in the previous workshop that in order for PyTorch to be able to calculate all of the gradients in the network, it needs to store all of the operations. So when we are doing for this network, we need to store every single operation that happened, because later we can use the chain rule to pass that gradient backwards where it needs to be. So we would start with W1 and x, and that would be our first node, and it's summation. So we need to remember both the operation and the operands. Then that outputs a product z. I put z here as it kind of makes it easier later to kind of play around with these things so that we can pass the gradients more easily later on. And so we take that z, which is just the summation of W1 and x, and then we're going to multiply it by W2, and then that's how we get our loss. So it's not really loss, it's just a variable called loss. So to start, we can also kind of decompose L, and so now it's just Z times W2. So the first question is, how do we get the derivative of W2? Yeah. So that is, so what is the, yeah, it is z, right? So it's just z. But then, what is the derivative of z with respect, or derivative of the loss with respect to z? Yep, that is correct. All right, and so now that we have that done, for backpropagation and the chain rule, it's very important that we store those calculated derivatives as well, because we are going to need that information to calculate the derivatives of the other elements in this backpropagation chain. So now that we have the derivative of the loss with respect to z and derivative of the loss with respect to W2, we can move on to the loss, derivative of the loss with respect to W1. So what is that? All right, so let's go back to the chain rule. It's actually very simple. So we had this chain rule, but we don't like it. So let's look at it in a better way. This is so much more better. It's much more intuitive. So we can imagine that we have three functions, right? We have z, x, and y. So in our case, W1 is going to be x, z is going to be the loss, and y is going to be z. So because that's confusing, I kind of changed it up in the next slide so that in our case, g is going to be W1, h is going to be the loss, and f is going to be z. Well, I was supposed to ask here what's what, but as we can see, so that now what we can do is based on that, right? So we replace W1 with G and Z with F and the loss with H. We can go back and now, well, I didn't show it for too long. So what will be the derivative of L with respect to W1? Somebody tell me here. W2. All right, so let's see. So first we take the derivative of the loss with respect to z. So what is that? Do we know? W2. That's correct. Now, what is W or derivative of z with respect to W1? So what is z? That's right. So what is the derivative of that with respect to W1? 1. And so you were right. So it is just going to be W2 multiplied by 1. And so no matter how many operations we have in a row, we could have 1,000 layers. All you do is you calculate derivative at one layer, you store it, you go back, you do this process, you store it, you go back, you do this process, you store it, and so on and so forth. So, and that is the genius part of the chain rule, because it makes calculating derivatives so much faster, especially with tensors, because if you look at this, we are just multiplying derivatives. And so because we will have many parameters and we will have many inputs, they're all going to be taking the matrix form. So now we can utilize GPU's fast efficiency with such operations to very quickly calculate the gradients. Okay, and then now you don't normally do this, especially PyTorch. It erases all the gradients for inputs. It is able to determine that because an input is usually not going to be part of a model's parameters. So once it detects that a certain tensor is not a model parameter, it's not going to store its gradient, but it will still, I think, compute it. But don't quote me on that. I don't know fully how PyTorch does its operations. But just to see here, for practice, the loss of derivative of L with respect to X is just going to be same thing, right? So W2 multiplied by 1. All right. Okay. So now we stored that. Can anybody tell me here the difference between how the gradient was passed on differently between multiplication and summation? You can think derivative of L is, what is derivative of L with respect to L? 1. Okay, so it's 1. So what happened, can you see some pattern for Z and W2? What are their respective derivatives? Yeah, the other, right? So the derivative for Z is going to be W2, right? Because if we very small incremental change of Z is going to result in a change of L that is W2. Same thing will go for, now this is just fantastic because I can't even see the screen anymore. Is there a way to cancel that out? Oh yeah, I think it's the arrow buttons. All right. Okay, so we see that for multiplication. Now what about the summation? So what is the derivative of L with respect to X and with respect to W1? We have it on the board. Yep. And with respect to W1, right? So, so it just passes on the gradient. So with summation, the gradient is just going to be equally passed on to the elements doing the summation. And we might be covering this in some more workshops. That is the reason why residual networks are great and allow for bigger debts, is because they equally pass the gradient, and that tackles another problem called vanishing gradients. But so here in short is that, so imagine a scenario x plus y. So L is equivalent to x plus y. So derivative of L with respect to x is going to be derivative of L with respect to x plus y multiplied by derivative of x plus y with respect to x. And yes, so the second term will always be equivalent to 1, which means that the previous gradient is always going to be passed on to the current derivative we're trying to calculate. Because the second term, as you can see, derivative of x plus y with respect to x is going to be 1. And that is always going to be the case for summations. And then, so you can see here. All right. And then for multiplication, so kind of same thing as we are just going to take the derivative of the loss with respect to x times y. And then we are going to multiply that by derivative of x times y with respect to x. And so we're going to use the gradient up in the chain towards the loss and then multiply it by the other value in our multiplication process. All right, questions? Yep. Yeah, so sorry, it's just because we're talking so much about gradients. Yeah, so a derivative. But it would be gradient. In this case, it is a derivative because it's really, we're just using a toy example. that only has like, if you can see, it's a toy example, has like 3 scalar values, whereas in a setting where we have a neural network in case, it's going to be some weight matrix multiplied by some input matrix. And so in that case, it's still going to be in matrix form. Thus, it's going to be a gradient rather than a derivative. But yeah. Yeah. So gradient is just many derivatives packed into one single vector. All right. So I hope you didn't have any burning questions, because take out a paper and a pencil. We're going to have a pop quiz. All right. All right. Okay. Let me know when everybody's ready. If you don't have a pencil, I have a pencil or a pen. All right. Okay. So let's imagine this scenario. We're going to have a network that has 3 weights and 1 bias, and it's going to have 3 inputs. And so for the result of that network and those inputs, we're going to produce a y that's going to be compared to y at the bottom. So y equals 7, that is the ground truth. And so we are going to compare it with what the model outputs. And now your goal is to propagate the gradients backwards, do backpropagation. So I already did some heavy lifting for, not heavy, but I already calculated the loss. It's 256, because when you multiply the weights by the input and add the bias, that's what you're going to get. So the goal is to get the gradients for W1, W2, W3, and B. You don't need to calculate the gradients for inputs because it's not necessary. We don't update them. And all right, I will be helping, so don't worry, you're not on your own. So we'll give like 20. Yeah, I have 20 minutes. I'm overkilling it, but hoping you all get it done in 10. So a tip or a hint, a square operation can just be looked at as one thing multiplying itself by itself. So you can use the standard formulation that we use for multiplication. Also, if you need a hint from one of the previous slides, let me know. Yeah, so the point is to do it backpropagation, not to do it. I know everybody here can take a partial derivative to this function, but the point is to start from the loss and then go backwards. Yep. Yep. So delta y is going to be the difference between y and y hat. And y hat is the prediction of our model. Yep. Oh, and my bad. Here it's 2 squared. So the last operation before L, that's squared. Okay. Yeah. Not square root of 256. You get 256 by squaring. 16 squared, yeah. All right. Does anybody think they have a solution? We're close. All right. You guys want me to go over it or continue working on it? All right. That's time's up. Nah, it's just easier to walk it through here, but oh, I think it's off. Hang on. All right. All right, so let's start off with the first loss. Very simple, right? So it's loss, derivative of the loss with respect to loss is equal to 1. So we do need the first element. It's always going to be 1, but you just start off with that. So now we need to move on to the second one, and that is derivative of loss with respect to delta y squared, right? And so L is really just delta y squared. So if we take the derivative of L with respect to that, we're just going to get 1. And I'm pretty sure we can make a more intuitive, actually no, we can't, never mind. All right, then we have the derivative of the loss with respect to delta y. So in this case, we already know we have that the loss is 2 or delta is going to be delta y squared, right? And so derivative of that is just going to be 2 delta y. So we don't really need to use the chain rule yet. Although we could have composed it. Oh yeah, never mind. All right. So then we need to move on to the second element in the chain, and that is y hat. So we did the derivative of, this marker sucks. So we did derivative of the loss with respect to delta y squared, which is 1, right? And then we move on to the next, which is derivative of the loss with respect to delta y, because loss can also be formulated as delta y squared. And the reason I put parentheses here is you can count this as just like one variable. So if we take the derivative to that, it's just going to be 2 delta y. Or if it's simple, like y bar. All right, now we need to take the derivative of y hat. And so y hat is really y, so y hat is going to be the output of the model. So I don't know if you can see. Oh, there you go. You can see with respect to y hat, right? So since we do know that delta y is equal to y minus y hat, and we know that the derivative of the loss with respect to delta y is going to be equal to 2 delta y. Given that what we know about backpropagation and the chain rule, what is this going to be? So if you can see, this is how we get delta y. And delta y is one element up in the chain, right? So what is going to be the loss of, or what is going to be derivative of L with respect to y hat? Yeah. Yep. Or it's negative. All right. All right. And here is how we can formulate that as well. So we just take the loss of y hat minus y, which is just our delta y, and then we multiply it by derivative of y hat minus y with respect to y hat. So the derivative of the loss with respect to y hat minus y, that is going to be 2 delta y. And so we don't need to compute that. We already stored it in the chain. So we use that value, and then we multiply it by derivative of y hat minus y with respect to y hat. And so that is just going to be 1. Or it should be negative 1. But the thing that confuses me still is that if I do torch backward, it doesn't take the negative. And it will compute with the positive values. You'll see in a second. All right. So now we have the loss of, or the derivative of y hat. What is our y hat? What is the, how do we get y hat? Yeah, so y hat, in our case, it's going to be the sum of n, and that goes to 3 of xn, and then plus the bias. Or for our use case, we need to kind of make it seem different, so we just do v1 x1 plus v2 x2 plus v3 x3 plus the bias. So let's start off with the derivative of L with respect to the bias. So now using the chain rule only, how can we get this? So let's first formulate this. How can we formulate this using the chain rule? What is the derivative of the loss with respect to bias? Yep. Right. And so what do we know here? We know this, and we don't know that, but that's very simple, right? Because we know our y hat. So in our case, the derivative of the loss with b is just going to get, actually, so here we can do, yeah, so that is going to just be the derivative of the loss with respect to y hat, which we have as 2 delta y multiplied by 1. Yeah. All right. So we have the first one. Now what is going to be the derivative of the loss with respect to W1, but formulate again as part of the chain rule? Somebody else, though. You answered too many questions. Yeah.
Delta L over delta y hat over
Yeah. Yep. That's right. And so you can see that if we do for W2, for W3, we're just going to get this multiplied by either x2 or x3. And now we can see, so I already put this in the remaining, right? And so these are the values. So it should be 160, 64, 32, and 32. And because we know that this is just going to be y hat, derivative of y hat is 2 delta y is 16, so that's just going to be 32 multiplied by x1, so that's going to be 160, and so on and so forth. Now, so you guys don't think I'm making this all up, making mistakes, how about we validate this using PyTorch? So in PyTorch, we are going to create 4 tensors. So one is going to be W, the other one is going to be B, which is bias. So W is our weights, B is our bias, X is going to be our inputs, and then Y is going to be the ground truth we're looking for. Very important few things. So when you are creating tensors for use where you need to compute gradient, it needs to be of type float 32. Because it cannot compute the gradient if it's not a float. It doesn't have to necessarily be float 32, but it must be a float, so it cannot be an integer. Then you also need that keyword requires grad, because if you don't specify requires grad equals true when defining a tensor, all of the operations you're going to do with your tensors, they're not going to track the gradient. So why does PyTorch do that? So if you remember all of this here, right? So can somebody tell me what is going to be the shape of gradient of some weight matrix? So say we have a weight matrix that has a shape of 5 by 5. So what is going to be the shape of that gradient? Exactly. Now, can you tell me why, not what is an issue with that, but what does that lead to when we do computations that track the gradients? Okay, so if we have a big network, especially large language models, so to just store a large language model, it doesn't take much, right? There are models that use like 1 or 2 GPUs, right? But then you hear that you need to require more, like 4 or 8. And the reason behind it is that for each, when PyTorch is computing the gradients, it stores all of those gradient tensors in memory. So you can think of it as that how many weights you have when computing the gradient, that's how much more memory you're going to have to use, because you will need to store the gradient matrices for all of them. And so sometimes that's why you want to not have requires grad equals true, because you may not want to store all of the gradients because it's memory intensive. And so now, since we covered that, let's move on to computing our loss. So if you remember, our loss is really just our inputs multiplied by the weight matrix. And then we're going to add some bias. We are going to subtract it from y, and then we're going to square it. All right. Oh yeah, so, and the reason we do transpose here is because we can see that our X matrix is going to be of the shape 1 and 3. And what is the shape of our W matrix as is when it's defined? How much?
1 by 3.
1 by 3, yes. So it has 1 row and 3 columns. And so the problem with that is that if we just do X times W, we are going to be multiplying matrices that have these dimensions. And so our inner dimensions of the product are not going to be compatible, because here we have a 3 and here we have a 1. But then if we do X, T, then the case is going to be like this. And so now what is going to be the resulting shape of the next matrix, of the product of these two? So these are the shapes, 1 by 1. Yep. but it is one by one because you still have to work. It's like a matrix that has like only one value, but it still needs to be in that shape. Right. And now same thing. Now we add the bias. So bias is just going to be an addition to that one element. And then we subtract y. So why do we do y hat minus y? Usually because, oh, so that's why the slides were incorrect. It is y hat minus y. So then the gradient is just going to be positive. So why do we do that? It's just the standard way that PyTorch does mean square error loss. You would put in first the prediction, and then you would put in the ground truth. And when you look at this, it doesn't really matter for the final output of the loss because you're squaring it, so the result is going to still be the same. All right. Oh. Okay, so now we have our loss, and you can see that once we print this tensor out, it has this grad function, and it's power backwards. So usually it's going to store the very next operation in the backpropagation chain. And we can see that the last thing we do with all of our values is we square them. So it's going to tell us what is the last operation you have. And usually, if probably some of you use neural networks, maybe for classification or for regression, if you use a sigmoid layer at the last piece of your network, you would see sigmoid backward. So that explains why you would see on the loss that thing right there. Then we do this function, loss.backward just did what we did. So what that does, it looks into this graph that it stores all of the gradient and all of the operations in this graph. It goes over that graph, and based on that graph, it's going to be updating all of the gradients for all of our matrices. And so once we run that, that computes the gradients, that assigns the gradients, and now if we print w.grad, it's going to print out our gradients of the W matrix. And if we go back to our slides, so we have 160, 64, and 32. And 160, 64, and 32. And then here it says bias is 32. And so bias is 32. Right. And yeah, so that's how PyTorch does that. Now, key part, and this is really just it's not that important, but usually when you're training a model, you need to also do zero grad, right? So say we compute these gradients, we update our network, but now we want to move on, right? Well, a very important part after this is to reset the gradients, and you just do this by doing oh, it doesn't have that function. Okay. So I guess it doesn't have it for default tensors, but usually what you would see is something to the likes of now we don't have an optimizer here, but the optimizer is really the thing that stores all of our weight matrices. And it has a built-in function called the zero grad. And what that function does, it goes over all of the matrices that the optimizer is storing and sets them back to zero. So after we update the network, we can start with fresh gradients. Because with gradient and backpropagation, we didn't cover this in the workshop, but say you have a W1 matrix, and say that it's affecting two different outputs, right? It could be working with two different values for some reason. What do you think happens when you do backpropagation? Say it does on X and it does on Z, and then the gradient is computed. What is going to happen with W1? What is going to be, and say here we have, I don't know, some L1 and then L2, right? So, and then we have derivative of L2 with respect to W1, and derivative of L1 with respect to W1. So what is going to be the total gradient for W1? Since now we have 2, because it's working with 2 different things. Yeah, exactly. So it's just going to accumulate gradients as it goes, and so that's why it's very important to reset your gradients, because if you don't, it's just going to accumulate and accumulate and accumulate, and your optimizer is just going to keep using a much bigger and bigger gradient, and so you're never going to be able to learn, or your model won't be. So with that being said, I think we concluded everything for the backpropagation, this workshop. Are there any questions? Yeah.
Is there any way to see the combination graph that PyTorch stores?
No, unfortunately it doesn't have. I was looking for that. I was so hoping to use it for this workshop, but it doesn't have any graph that stores all of the gradients, but that would be lovely if it did. But I'm pretty sure there's tools out there, or it would be very simple for you to do it. You would just have to adjust the tensor so that it kind of stores operations in the way you like it to be, and so then you can make your own graphs, but unfortunately not, no. Right. That's no more questions. Next workshop, we'll be covering what do we do with this now. And yeah, there is basic gradient descent, but we're going to cover limitations of it. Why do we use different algorithms? They're very similar, but gradient descent that you saw on these slides is heavily adjusted. If we go back to... There we go. So this is going to be the topic of the next workshop. Why this doesn't really work with real world data, and what do we need to do with it so that we can make it work. All right. Thank you.